I'm fixing my homemade helicopter after the drive shaft failed. The last video had a massive response in the comments, which was really helpful. Thank you very much for all your input. There are a few people with concerns, as you might expect, but it was constructive criticism. When someone disagrees with me and says an idea won't work because of X, Y, and Z, I need to try and find out which is right. I'll address this later in the video, but first I was encouraged to reinstall an overrun clutch, and this is what I'm going to do. This is the pulley I made without the overrun, and this is the one I made with an overrun. You can see the size difference and the problem with using the internal sprag bearings in the new pulley. Having taken out the drive, there are a few things I've noticed. Firstly, this damage to the belt retaining flange. Secondly, the poor surface condition of the drive spindle where the top bearing is located. Both of these damaged components tell me the top bearing seized at some point. It's not seized now, but it feels notchy. I don't know why this seized or when it seized. I would assume it seized during the technical event, but it could have seized before that and I didn't know. My gut feeling is it seized during the technical event. Possibly during one of the drive impacts. There were no indications of a problem before that day. Now here is something that really surprised me. Take a close look at the teeth on this pulley. They are bent. Compare it to the old one and you can just about see the teeth aren't straight anymore. Looking at the direction the engine rotates, the teeth are bent in the opposite direction to the engine torque. This has happened when the drive shaft briefly jammed and the rotor inertia forced it to carry on. This unfortunately means the belts took an impact force high enough to bend those teeth. I'm amazed they did that without breaking. I think that shows how strong these belts are, but they have been stressed. I'm worried about the belts now, and that's not the only thing I'm worried about. All of the drive will have taken a significant impact. Pulleys, shafts, rotor hubs and the blades, all of which need to be examined. To replace the belts will cost £600, a significant sum of money. One comment I had from a well-known helicopter builder was to perhaps use a ratchet mechanism as an overrun clutch. Let's have a look at a ratchet and see how they work. Seems to be just a bit of steel that jams the tooth spindle in one direction and not in the other. I might have trouble fitting this type inside my pulley. Here is another type that has the teeth on the outside and the inner one has the corresponding teeth that locks via a cam type arrangement. Pretty compact. I'll have a think about how this type of design could be incorporated. Something else I just noticed is that the drive spindle is also twisted. I can just about make out the keyway at the bottom has a twist at the end. All the parts really took an impact, which is such a shame, and they're going to have to be remade, but it does show what force they can take. This EN8 keyed shaft is only 20mm diameter, and yet it took the impact high enough to bend all those teeth on the aluminium pulley. I wouldn't have guessed it to be that way around. I think all this damage demonstrates the amount of stored energy there is in a rotor system. Helicopters are just crazy machines. Like them or not, you can't fail to be intrigued by them. In the last video, I talked about the idea to use a square telescopic aluminium drive shaft separated by flat cage needle rollers. I had a few comments saying that aluminium should not be used as a drive shaft material because of the material's resistance to fatigue. Let's say that the engine produces 2 power pulses every rotation. There are 2 cylinders and each one fires during one rotation of the crankshaft. The engine during normal operation is running at 5,500 RPM, so during 1 hour of use there are 660,000 power pulses from the pistons. If we look at data for 6061 T6, we can see that if the stress is kept below 95 MPa, then testing data proves it can endure 500 million cycles at this stress. This drive shaft would then be safe to use for 757 hours of operation. The 95 MPa figure is for tensile stress, whereas mine is being used in shear, That means it should be taken as 65% tensile or 62 MPa. That is the figure we need to go by. So the next thing we need to know is what is the stress my dry shaft is under. Thanks to Martin Garrish for assisting me with this calculation, and here it is. According to the calculation, to keep the dry shaft stress below 62 MPa, the torque cannot exceed 586 pounds-feet. The maximum constant torque this engine produces is 55 pounds-feet, a factor of safety of 10.6 in this case. Now the 55 pounds-feet is the maximum constant torque. What I need to know is what are the spikes. If I had to make a guess, I would say they're around 100 pounds-feet, but guessing isn't good enough. I want to know what they actually are. The next question is, how am I going to measure what the spikes are? It is possible to measure torque with strain gauges. You can get strain gauges that work on round drive shafts to measure torque. The trouble is, they are on a revolving part and you need a way to transmit the data as it cannot be hardwired. A square section drive shaft might also add to the problem. Another way I've thought of is to use a strain gauge on another part of the drive that doesn't rotate. It could be mounted somewhere that bends with the torque, and then I can recreate this torque with a simple torque wrench on the drive shaft. You can get something called a load cell, where the gauges are already mounted and wired inside a block of material. All you need to do is mount it to somewhere that bends under torque. I think this could give me some accurate data without being too expensive. While I'm thinking about that, I have come across some needle roller sprag bearings. That could be a way to give me an overrun clutch still using the smaller drive pulley. The concern here is the needle rollers drive the parts through friction and a press fit. There are no keyways, which is good in the sense of no stress risers, but will a press fit be enough to drive the 55 pounds-feet of torque load and above? I expect some of you will disagree with me here, but I think it will. Thinking about how this works, the needle rollers jam against the inner and outer wall of what they are pressed into according to how much torque is being applied. If both parts were steel, data shows each needle roller can drive 48 pounds-feet of torque. I have 5 to install, but the pulley is not steel, it's aluminium, and this is going to reduce the amount of friction from the compressive load. The aluminium will give more than steel and grip will be lost to some degree. If it got hot, then it definitely wouldn't work because aluminium expands at a greater rate than steel. I had a problem with this when I made the clutch. That had a pressed steel liner and heat expansion caused slippage. I secured the liner with bolts after that. Going back to the drive shaft, there are other potential issues with my design, and that has been pointed out in the comments. I'll address this in the next video. Quick update on the flying boat. I've got the wing spar mounting tubes welded into the frame with a 4-degree dihedral. I've made 2 of the wing spars. They are 76mm diameter, 1.6mm wall, but I have machined inserts to double the wall thickness where they mount. With the long spars mounted, I can now see there is too much flex in the fiberglass hull and aluminium frame I made. This is not satisfactory and needs to be rectified. I can strengthen this by adding struts to locate off the ribs of the hull. Adding struts I think is going to work. Seeing a wing on is quite exciting and really quite daunting when you look at the size of it, something you really can't appreciate through a video. I sit in the machine I have created wondering what on earth I'm doing. I must be crazy. I thought that about the helicopter too, but that turned out to be an awesome toy when it was working. Hopefully this will work too, but it's certainly not guaranteed. The forward position of the pilot will certainly give quite an uninterrupted view. It's going to take some nerve when testing day comes. Still a lot to do, but it's starting to get exciting. Thanks for watching.